Okay, so now let us start today's lecture. Okay, so now the first thing I'd like to do is to remind you of the place where on Canvas where you can find, okay, so where you can find all the previous year's exam problems. Okay, so if you log into your Canvas panel, you're going to see a panel like this, and this is the Math 3304. This is the web page for our course. Okay, so for our section during Canvas on Canvas. But if you want to look at student resources, you should click the left column courses. Okay, so you click courses, and then you kind of scroll down. Okay, scroll down to here. There's all courses. Okay, so now as long as you have all courses, you click browse more courses. Okay, so browse more courses, and then you're going to see student resources for student Math 3304 elementary differential equation. Okay, so you click there. Okay, so you click there. Then you're going to see a Laplace transform short table, calculators. Okay, so calculator policy, integral formulas, as well as past year's exam problems. Okay, so that answers some questions raised by you, that where to find these student resources webpage. Okay, so remember it's a courses, and then browse more courses, courses, all courses. Okay, so all courses, and then browse more courses, and then you're going to see student resource page, and just click there. Okay, so that's kind of the way how you find. Okay, so I have recorded this instruction into today's video. Okay, so if anybody else has questions on this, you will watch the video, and you're going to see what's happening to the student resources. Okay, so now let's start today's lecture. Okay, so we're going to continue with what we have been doing last lecture, right? So now in the previous lecture, we've been doing something about first order equations, right? So that was all about first order equations, right? So it was a first order equation. For example, okay, so for example, we've been solving, okay, so we've been trying to solve a differential equation of the form dy over dt, right? So is fty. This is a general first order equation. But such a general first order equation may take the form, okay, may take the form dy over, okay, so dy over dt is equal to m of t, right? So divided by n of y. This is what we call a separable form, right? So that we call it a separable form. Now we've been talking about how to solve a differential equation in separable form, right? So talking about how to solve a differential equation in separable form. Now this is the first order equation. Okay, so then very important thing for differential equations is that we've been talking about linear, right? So let me remind you again that by a linear ODE, right? So by a linear differential equation, it means an equation of the form y derivative n plus, okay, so let me say an of t, right? So an minus 1 of t, y derivative of n minus 1 plus dot dot dot. Okay, so plus dot 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 plus a1 of t y prime plus a0 of t of y is equal to g of t, right? So this is what we say by a general linear nth order equation. Now, important thing is that these coefficients are independent of y, and you don't have yn derivative squared or anything like that. Everything is about y, and there is a non-homogeneous term, g of t, on the right-hand side of this equation, right? On the right-hand side of this equation. So that's kind of the linear. Okay, so the linear nth order differential equations, right? So now let's look at first order equation. If we focus ourselves on first order equation, how does a first order linear equation like that look like? So let's say first order linear equation, right? So how does the first order ODE linear look like? Well, you can follow this trend, this general form. So it will look like a1 of ty prime plus a0 of t is equal to g of t, something like this, right? So that's sorry. So there's the derivative y, right? So let me make it more clear. Okay, so let me make it more clear, right? So that's a0 of t of y is equal to. So that's kind of a general first order linear ordinary differential equations, right? So now here you can see that there are two coefficients, a1 and a0. Okay, so a1 and a0, right? So that's a general first order linear equation. Now I claim that you can turn this equation into the form y prime, right? So plus a0 of t divided by a1 of t multiplied by y is equal to g of t divided by a1 of t. You can divide both sides by a1 of t, right? So that the advantage of doing this procedure is that you have rescaled the derivative in front of y to be just, okay, to be just 1, right? So that's the coefficient is 1 here, and it might get rid of, I mean, it will change these two coefficients. So the general form of the first order linear equations, okay, so that's called first order, okay, so that's called first order linear equations. That's going to look like y prime plus, okay, so p of t of y is equal to q of t, where the p of t is this part, right? So we're going to set this part to be your p of t, and you're going to set this part to be your q of t, right? So that's p and q star. If you write this equation in this form, then we're going to call it, okay? So if you write an equation in this form, then you're going to call it, this is very important. We're going to say that this differential equation is being written in standard form, By standard form, it means that the coefficient, okay, so this is very, very important. Okay, so please make sure you get to this part, is that by standard form, it means the coefficient in front of the highest derivative. So we are going to, in particular, look at the highest derivative. Okay, so the coefficient in front of the highest derivative is 1. Okay, so coefficient in front of the highest derivative is 1. So let me say it here. Okay, so in front, okay, so coefficient in front of highest derivative, right, so is equal to, is 1. So that's why we call it a standard form. The standard form, you can see that it simplifies the equation pretty much. Okay, so this is a first order linear ODE, or maybe I'll write it as dy over dt plus p of t of y is equal to q of t, right? So that's kind of the, we're going to say that this is the coefficient of the, it's a first order linear ordinary differential equation, but rather we have been writing it in standard form, right? We've been writing it in standard form. Okay, so now with this at hand, okay, we're going to kind of be working with how to solve first order equation which is linear, right? So how to solve a first order equation which is linear. So we've been seeing that this kind of equation in general is nonlinear. So that's in general, okay, so right? So this kind of equation in general is a nonlinear, right? So if it is a nonlinear, right? So then the only possibility is to use integration, the separation of variables. If it cannot be used by separation of variables, simply it cannot be solved, right? So you won't see such problem. But rather, if you have like a linear first order equation, then we're going to talk about another method of solving this equation. We're going to call it integrating factors. Okay, so we're going to call it integrating factor method. Right, so we're going to call integrating factor. What's the integrating factor method? Well, here I'm going to give you an example. Okay, so I'm talking about example. This example is from one of the previous year's exam problems. It was taken from fall semester 2015, the exam 1, problem number 1. Okay, so as I said many times during these lectures, it's a very important tip for you to do well on the exams of this class, is that whenever you are on an exam, please read the problem carefully. Okay, so understand what the problem is asking for. Okay, so if you don't understand what the problem is asking for, then even if you solve the problem, you might lose points just because of that. Okay, so please make sure you understand the problem. Okay, so and read the problem instruction as carefully as you can. Okay, so this problem says, can you find a value? Okay, so it's not just solving an equation, but rather we want to find a value of y0 for which the solution of such an initial value problem, something like this, with the initial value can approach 0 as t goes to infinity. So we want to have something approaching 0 as t goes to infinity. So the example, okay, so this example have such an equation. Okay, so the equation takes the form ty prime. Okay, so it's like ty prime minus y, right? So ty prime minus y is equal to t squared e power minus t, right? So say it's equal to, right? So it is equal to t squared, right? So t squared e power minus t, right? So with a given, okay, so with a given initial condition, okay, so with a given initial condition, right? So with a given initial condition that y of 0, right? So y of 0, just a moment. Okay, so with a given initial condition that here the problem says, so okay, so the problem says y of 1 is equal to y0, right? So that's kind of saying that y of 1 is equal to y0, right? So the y0 is a certain given initial condition. Okay, so y0 is a certain given initial condition. Okay, so you're going to have the problem is going to somehow look like this, right? So problem is going to somehow look like this. So then, of course, you want to try to see if you can solve this equation, right? So try to see if you can solve this equation. How do we solve it? Well, first of all, you can see that this is a first order linear equation. So why did you justify it? How do you justify it? Well, you justify it by this form of linear ODEs. There are coefficients that must be linear, right? So therefore, you can see this is the coefficient. This one is linear. This is a linear non-homogeneous equation, right? So it's a linear non-homogeneous equation. How do you solve it? Well, I have to say that the first step is always to turn your equation in standard form. Okay, so you cannot ignore that step. This is a very important step that you must turn your equation in a standard form. Okay, so you must turn your equation in a standard form. So that means, for example, this equation is this equation in standard form. Anybody can answer my question? I mean, please do not hesitate to interact with me during the lectures. This is rather welcome. Okay, so and don't worry if you make mistakes. Can anybody tell me if this is a how do you think about this one? Is this a standard form? Anybody has idea? Just say it. Okay, so you may not just need to type in the chat. You can just unmute yourself and say it, and everybody will hear it. But it's okay. Yeah, we see it. It's somebody says no. That's good. Okay, so because standard form is that leading coefficient. As I said, coefficient in front of the leading highest derivative must be 1. So that means this one in a standard form. Okay, so in a standard form, right? So in a standard form must look like y prime minus 1 over t of y is equal to t e power minus c. So you divide everything by t. This is very important. And whenever you see a first order linear equation, you must turn this equation in a standard form. Okay, so that's very important. Whenever you see a first order linear equation, please turn the equation in a standard form. This is very important. As long as you turn a standard form, how are you going to solve this equation? Well, is there any method that you really can solve this equation? Well, in a standard form, it looks like, for example, assume, right? So assume this equation, let's say, maybe I'll write it here. Okay, so assume this equation is like y prime is t e power minus t. You don't have this bordering term. This one is rather bordering term. Then you're going to just see that y is just the integral of e minus t multiplied by t, maybe dt, right? So it's kind of very simple business. But here you don't have this, all right? So you don't have this. We kind of just, you don't have this paradigm, right? So this is maybe erase it, right? So you never had this such a nice paradigm that you are able to just directly integrate your differential equation. You're not able to do that. So then what means is that you have to kind of find a way to get rid of this -1/t multiplied by y term, right? So get rid of this term. How are you going to get rid of this term? Well, let's consider a function, okay, mu of t. Okay, so is equal to e power of the integral -1/t of dt. Okay, so let me consider this function. Okay, so let me consider this function. Now, people is going to tell me, okay, ask me that it looks like this is kind of rather sophisticated function, but how you can come up with such a function, right? So let's look at first observe. Okay, let's first observe that this coefficient, this integral, okay, so it's like e to the power of an integral, which is reasonable. You're going to calculate the integral first and raise everything to e to the power. So that's a reasonable prediction. But what's the integrand, right? So what function you're integrating? Well, you're just integrating this function. This 1/t is the same thing as the 1/t here. So, but it is not the -1 here. So it means that this 1/t somehow comes from the equation in standard form. So you have to first, okay, you have to first turn your equation in standard form, and then you're going to have the coefficient 1/t. You put the same coefficient here, you integrate it, and then raise everything. That when you integrate, you're going to end up with a function of t, and you raise everything to exponential. Then that's it. And moreover, it is also observed that when I write this integral, I have not been doing anything, right? So it's just an antiderivative. So you just find the integral by doing an antiderivative. That's it, right? So you just find the integral by doing an antiderivative. That's it, right? So you can just do an antiderivative. So why is that the case? Well, if you consider, okay, so let me consider d by dt. Okay, so of the function mu of t multiplied by y, I'm going to consider this. So how do I, so what I'm doing is that I multiply this mu of t with the function y and then take a derivative. And what I'm going to have? Well, by classical principle of product, or derivative of product, right, product rule, it's going to tell you that this is actually mu prime of t multiplied by y, right? So plus mu of t multiplied by y prime. This is just a derivative rule, right? This is just derivative rule. Now, how can you calculate? Okay, so y prime is easy, right? So, but how do you calculate mu prime of t? Well, if mu of t is something like this, right? So, how do you calculate mu prime of t? Well, mu prime of t can be calculated by chain rule. Why is it chain rule? Because we can treat mu of t as a function, right? So that's a kind of e to the power of, let's say, f of t. Right, so it's a function. So by chain rule, it's going to be just e to the power of f of t multiplied by f prime of t. Is that good, right? So the e to the power of t is just the mu of t itself. So we don't have to really worry about this e to the power f of t. It is going to be just what you already had. So that's mu of t, right? So it's just going to be just what you already had there, right? So what you already had there. But what is f? Well, the f is just the integral. If you have a function that's an antiderivative, then the derivative of the antiderivative recovers the factor, right? So it is going to recover the factor. So after this analysis, you are going to see that f prime of t is going to just recover, right? So it's going to just recover the -1/t factor as in the integrand, As long as you have this, you can see that this is actually mu of t multiplied by -1/t of y plus, so let's say this is the product here, mu of t of y prime. So indeed, you come up with mu of t multiplied by y prime minus 1/t of y. And what is y prime minus 1/t of y? It is given, right? So you're going to be given such a function, right? So that's you're going to be given such a function. So that's actually is going to be, okay, so that's actually is going to be such a function, which is mu of t, right? So mu of t multiplied by t e power minus t. So that's kind of, you get such a very nice relation, right? So you get such a very nice relation between this mu of t multiplied by y and derivative as well as something, right? So now let's kind of realize everything in practice, right? So if you take this mu of t is equal to e power the integral, okay, so minus 1 over t dt, this one can actually be calculated, right? So what is the integral of 1 over t? So it's e power minus the logarithm of t, right? So some people is going to ask me, why don't I use the logarithm absolute value of t? Because y1 is y0, so that means t is greater than 1, t is greater than 1, so that you start everything from 1, right? So this is actually 1 over t, right? So because e power ln t is t, this is minus 1, so 1 over t. So you can see that easily that the mu prime of t is minus 2 over t squared, right? 2 over t squared. And this actually follows this general principle. Mu prime of t is mu t multiplied. So mu t is actually equal to 1 over t. So you just multiply everything. That's you're going to see that this is kind of 1 over t squared. Sorry, this here is 1 over t squared, right? So, right. So here is 1 over t squared. So you have this, and our general principle says that you want to multiply mu of t with y, right? So that means d by dt of the thing that is y over t. And this simply is going to be given by this chain rule that we have already calculated here. It is actually, or you can just use a direct chain rule. It's minus 1 over t squared of y plus 1 over t of y prime. And then you can see that this is nothing but 1 over t of y prime minus y over t. Y over t. And y prime minus y over t is just t e power minus t. So this is actually 1 over t multiplied by t e power minus t. So that's e power minus t. So that's kind of the way how you get relation, right? So, and why it is, what's the philosophy behind it? Well, the philosophy behind it is very simple. You are not able to integrate such a linear equation if you do have this term. So you have to get rid of this term. How do you get rid of this term? We have created such a mu of t, which is an exponential power of the integral of this coefficient in your in your standard form, and thus one satisfies this important identity, which kind of tells us, for example, here that very trickily, right? So in a very tricky way, that d by dt of the not the function y, but the function y multiplied by mu of t, and multiplied by mu of t is divided by t, you're going to recover something that you really can integrate. So from here you can see that at least y over t is like the integral of e power minus t just by fundamental theorem of calculus. So that's minus e power minus t plus constant, which is going to tell you that y of t is equal to minus t times e power minus t plus constant multiplied by t. So you're going to have an equation of a solution of this form, right? So you're going to have a solution of this form, right? So you're going to have, this is the general solution of your problem. Okay, so you can see that this whole method is like the key point in this whole method is like you introduce this mu of t, right? So why do you need this mu of t? Well, by this general analysis, it kind of tells us that as long as you have mu of t is raised by the standard form, you take the coefficient integrated, mu prime of t must be related to mu of t by the factors in this, which is just the coefficient in the standard form. And if you have that factor, you multiply this mu of t by y, you take a derivative, then it's going to come up with the mu of t multiplied by the right-hand side, which is this coefficient, is just this coefficient, right? So these two are the same, right? So, and these two are the same. So that's kind of just make full use of each of the coefficients in the equation in a standard form, right? So that's kind of tells you that this mu of t, right? So this mu of t is actually like a catalyst, right? So you study chemistry. In chemistry, they tell you that in order to create a chemical reaction, you sometimes, most of the time, you need a catalyst, right? So this one is like a catalyst. When your mu of t is thrown into the equation, the non-integrable, right? So without this factor, this equation is easily to be integrated. But with this factor, it looks like the equation is not so easy to integrate. But it doesn't matter. With the catalyst, the mu, when you multiply by mu, you can integrate easily, like what we have here. You multiply by mu, you can have a derivative that's very explicit. and you can integrate easily. So that's why this factor is called an integrating factor. Okay, so that's why this factor is called an integrating factor. Okay, so this factor is called an integrating factor. The very important thing. Okay, so that's why this today's lecture is also called the integrating factor method. Okay, so we have two keywords. Okay, so we have two keywords being mentioned in today's lecture, which I would like to say are very important. Okay, so it is very important to remind you that the class is going to be our class. Okay, ordinary differential equation is going to be like the following: that every lecture, okay, every lecture has its own keyword. Usually just one or two keywords. If you remember those keywords, you get the point of the whole lectures, right? So you're going to have a good understanding of the course. For example, today there are two key words. One is standard form. By standard form, it means the coefficient in front of the leading coefficient is 1, right? Leading derivative of the equation is 1. The coefficient in front of the leading derivative of the equation is 1. And another keyword we talked about today is called integrating factor. Remember, integrating factor follows from standard form. You put the equation in standard form, you read the coefficient in front of y instead of y prime. Y prime has coefficient 1. You read the coefficient in front of y, and as long as you have that coefficient integrated by antiderivative, you just don't have to integrate it in a fixed way, just to find the antiderivative, and then multiply by e power of this object, right? So multiply by e power of this object. That's going to be called an integrating factor, right? So there are two words in this terminology. One is integrating, which is pretty easy to understand because this mu of t. This mu of t is just something that helps you to integrate. So that's kind of why it's integrated. Why it's called a factor? Well, the factor is also easy to understand because the reason why we're going to call it a factor is because it's really a factor. This is a factor that you have to multiply this factor with respect to the original unknown function in order to create a chain of equalities that you can easily integrate. So that's why it's called integrating factor. And the whole method, okay, so the method introduced here is called an integrating factor method. Okay, so the method introduced here is called an integrating factor method. Okay, now let me come back. Okay, so let me come back to the problem, right? So the problem is saying that it's not finished, right? So that's why I emphasized many times that everybody must be looking at the problem very, very carefully, right? So do not just, let's say you see an equation, you solve it, and then you think everything is fine. That's not enough, right? So it's not enough to just solve an equation, but rather you have to understand what is required in the problem. The problem says that, can you find some value of initial values such that this equation is going to approach 0? So that basically means, okay, so first of all, this is a general solution. It's not enough because the problem is an initial value problem. You have to put initial value y1 there. So that means if you want to put y1 there, so y1 is equal to minus e power minus 1 plus c is going to be of y0. So the constant is actually e power minus 1 plus y0. So that's the constant. As long as you have the constant, right? So some people ask, well, it depends on y0, but y0 is something we are asking for, right? So let's say you have the constant. As long as you have the constant, you can see that y of t is minus t e power minus t, right? So minus t e power plus ct, and c is actually plus e power minus 1 plus y0 of t, so that's plus ct. So that's the kind of actually the particular solution in terms of y0. And now you come back to the question. The question just says, I want the solution to approach 0 as t goes to infinity. I want a solution to approach 0 as t goes to infinity. That's it, right? So how do I have this solution approach 0? Well, in order this solution, when is this solution approaching 0? Well, you can see that, for example, as t goes to infinity, t becomes large. What's the limit of this term? Minus t e power minus t goes to what? Anybody can give me your answer? I want you to participate. If t goes to 0, what's the limit of minus t e power minus t? Anybody has idea? Don't hesitate to say anything. I mean, let everybody hear. It doesn't matter. Don't be shy. Can you tell me what's the limit as t go to infinity of t e power minus t from your calculus. What's that limit? Anyone has idea? You see, t is a growing polynomial, and e power t is decreasing exponentially. So you're multiplying something increasing, something decreasing, what will be the limit? The limit is 0 because the exponentials is always going to kill any polynomial growth. The limit is 0, right? So that means as t goes to infinity, you don't really have to worry about this term. Just worried about this term. If e power, okay, suppose e power minus 1 plus y0 is positive, then this limit is going to grow to plus infinity as t goes to infinity. If e power minus 1 plus y0 is negative, the limit is going down to minus infinity as t goes to infinity. So both scenarios are not what you exactly want to have, but rather in order, right? So let's say in order that y of t goes to 0 as t goes to infinity, we just want e power minus 1 plus y0 is 0. You don't want this coefficient to be 0, and the only term is this one. So that kind of gives you the solution y0 is minus e power minus 1. Right? So that's the solution, is minus e power minus 1, which is the solution. Right? So and if you look at the way how they solve this problem, it's indeed the case. The solution finally is minus 1 over e. Right? So that's kind of completely answers the whole question. Remember, in order to completely answer the whole question, you have to look through the requirements of the problem very carefully before you determine what you should do. Okay, so before you determine what you should do. So that's kind of a very important thing for this lecture. Okay, so thus we have already discussed this integrating factor method. Okay, integrating factor method. So let me just briefly summarize what's the integrating factor method, right? So, okay, so let me just briefly summarize the idea behind this integrating factor method, right? So let's say summarize. Okay, so I have to turn it off. So let's say summary. Okay, I wrote this and make mistake again. Okay, so. Right, so what's the summary? Well, the summary is that we're going to do an integrating factor method, right? So integrating factor method. First step in the integrating factor method, right? So step 1 is to turn everything in a standard form. So y prime, right? So it must, in a standard form, the situation must look like, right? So it must look like, just to make sure you're still there. Okay, so just to make sure that you're still there and I'm recording. Okay, so we're going to look like, right? So if you kind of turn this equation in a standard form, okay, so then you're going to look like, right? So it's going to look like y prime, right? So y prime plus, right? So plus p of t of y is equal to q of t. So that's kind of an equation in standard form, right? So that's kind of an equation in standard form. We have an equation in a standard form. Okay, so as long as the equation is already in a standard form, the step 2 is to calculate the integrating factor. So which means mu of t is e power integral of the p of t dt. That's it, right? So you're going to must use this integrating factor. So this is calculating the integrating, right? So this is calculating the integrating factor. As long as you have calculated this integrating factor, right? So this p is just this p, so they're the same p. So as long as you calculate the integrating factor, the third step is to consider d by dt, right? So of the mu of t multiplied by y. And then as long as you have this, you're going to see that you're able to calculate this derivative by using this equation as well as the integrating factor. So that's the essence of this integrating factor method, right? So that's a summary of the essence of this integrating factor method. And why it works? Well, it works because we have explained such an idea that as long as you have the mu of t, you take a derivative, you by the product rule, you'll always be able to recover the original equation, but this original equation in standard form. You recover this original equation, but in standard form. As long as you have that, you're able to continue with your integration. So that's kind of the 3 steps we summarized for the integrating factor method. Okay, integrating factor method. Okay, so now before I continue, let me make a few remarks. Okay, so let me make a few remarks before I continue with these lectures. Okay, so the first remark I would like to say is that the integrating factor mu of t is actually chosen up to a multiplicative constant. So what does that mean? Well, it means that, for example, this mu of t, okay, so the remarks, okay, so let me make a few remarks here. Okay, so let me make a few remarks here. First of all, you must observe that mu of t is e power the integral of p of t dt. But this is an antiderivative, so it might happen that this is actually e power of p of t dt plus constant. This is again an antiderivative. Both are antiderivatives, right? So both are antiderivative. So if you have if the situation is like that, then it means that actually this is actually c times e power the integral pt dt, because e power c is actually a multiplicative constant. So that means the integrating factor is only determined up to constants, right? So let's say if mu t is an integrating factor, 2 mu t is also an integrating factor. It's actually not quite uniquely determined, right? So you can multiply any constant you like, you're still multiplying creating integrating factor. So that's why I say here that integrating factor is chosen up to a multiplicative constant. Okay, so now the second thing I want to say is that you must check, right? So you must check d by dt of mu t multiplied by y. As I just said, in the step, you have to calculate this. And once you calculate this, you're going to see a scenario, which is pretty much like what I'm having here, right? So what I'm having here, that you're going to produce, okay, you're going to produce your original equation. You're going to produce your original equation. Now, as long as you produce your original equation, you're able to continue with your integration, and so that gives you the integration. Now, the third thing I want to mention, okay, so the third thing I want to mention is regarding how you solve this particular problem. Okay, so let's say you have this problem. Okay, so let's come back to this problem. Okay, so now for example, okay, so for example, here I have calculated, so I have calculated d by dt, right? So of y over t is actually equal, so according to my calculation, it is equal to e power minus t. Good for everybody? Okay, so it kind of tells us that this derivative is e power minus t. So then from here, I'm going to do a naive thinking. Y over t is minus e power minus t, which is antiderivative plus constant. Then I fill in the constant by the initial value. That's a good idea, right? So that's a good idea. But you can also do it in the following way. If you have a derivative equal to a function, then you can apply the fundamental theorem of calculus. Okay, so right, so then you can apply the fundamental theorem of calculus. By applying the fundamental theorem of calculus, it simply tells you that y over t minus, okay, so this yt is t, right? So yt over t minus y1 over 1. So I'm treating this yt over t as a function. This fundamental theorem of calculus says that this is the integral. Now I have a fixed integral. I'm fixing my integral domains. So from 1 to t of e power minus t dt. Why I'm having this situation? Because the initial values for my problem started from 1. It doesn't start from 0. So I have to integrate starting from initial value to the t. And you integrate that one, this is actually minus e power minus t when t is equal to t, right? So as well as t equal to 1. So you can see that this is 1 minus e power minus t. Is that good for everybody, right? So that's 1 minus e power minus t. And what is y1? Well, according to the problem, it just says that y1 is y0. So this y1 is just equal to y0. So you're going to have an identity saying that y of t divided by t is equal to what? Well, you can move this term to the right so that you're going to have 1 minus e power minus t plus of y0. And that's actually tell you that y of t is actually minus t times e power minus t plus let's say so here this is t equal to 1 is not minus 1, right? So when t equal to 1, the situation here is that this is going to be, okay, this is going to be e power minus 1, right? So e power minus 1. So you're going to have an e power minus 1, right? So you're going to have an e power minus 1 here, right? So you're going to have an e power minus 1 here, right? So let's say e power minus 1. Therefore, this is e power minus 1 plus y0 multiplied by t. That's the solution. It's a good family. Okay, so now from this calculation, you can see, okay, so let me ask a question. Have we ever used the fitting constants? We have never done this. So this kind of, in this method, we never use the constant form. I mean, we don't ever, never jump to general solutions. We can kind of get the particular solutions directly by saying that we are using a fundamental theorem of calculus. I integrated from the initial value to the current value and use this derivative. I kind of recovers everything automatically, like in one step. I don't ever even need the integrate the general solution and fit into the general solution. So that's why I say sometimes, I mean, now you're beginners, right? So this moment, you're the beginners of this semester, you just have started this course. But as long as you have become proficient, right? So you become learners of ordinary differential equation, you have to be flexible. Sometimes you can see that I don't even need to calculate constants. I can just integrate within a certain domain using fundamental theorem of calculus. Okay, so that's kind of a remark I would like to mention. Okay, so I would like to mention before I continue with the lectures. Okay, so that's kind of a nice remark before I continue with the lecture. Let me show you, okay, so let me show you just one more example. For semester 2015, the exam final number 3, right? So let's say for semester 2015, the exam final number 3. Okay, so okay, so this kind of problem, okay, so this kind of problem is similar, right? So you can see number 3. Okay, so can you find a general solution of the following differential equation? Now let me, since we have mentioned both methods, like the separation of variables and integrating factors, you have to really know how to choose the method, because on an exam, they're not going to tell you anything about which method you should use. So what's the criteria? Now, the criteria is very simple. If the equation is first order linear, then like what happens here, this is a first order linear equation, then you're going to use integrating factor. If it is a first order nonlinear equation, you must use separation of variables. But however, if even for first order linear equations, sometimes you are still able to use separation of variables. So separation of variables is more general than integrating factor. But sometimes on an exam, I can tell you that they're going to specifically say, please use the method of integrating factor. If that is the case, then you have to show the integrating factor. So for example, this problem, how do you use integrating factor? Well, it's very simple. You just write the equation in standard form. This is the standard form, right? Remember, leading coefficient is 1. Now, this coefficient is what you want to do in the integrating factor. P of t is the integrating factor. You put it there, you get integrating factor. As I said, you must multiply the integrating factor with y and take a derivative. So this is multiplying integrating factor with y. Take a derivative. After some calculation, you get this function. And therefore, this e power minus t over 2 of y is just antiderivative of this function plus constant, from which you are going to be able to find a solution. So that's kind of a very simple problem on one of our exam questions. Okay, so on one of our exam questions. Okay, so here, as I just mentioned, that on the exam, they're not going to exactly tell you which method you should use, right? They're not going to tell you which method you should use, but rather you are expected, okay, so you are expected to choose the right method by yourself, okay, choose the right method by yourself. However, this is not a hard task if we have clues, right? So what are the clues? Well, the clues are, for example, if you see first order linear equations, maybe you should try integrating factors. But if you see first order nonlinear equations, maybe you should try separation of variables. However, sometimes, even for first order linear equations, you can still use separation of variables. Okay, so let's just take the last 2 minutes Look at this problem. Okay, so it was also from one of the previous year's exam. It says y prime minus sine t of y squared is 0 with initial condition. Is this problem a linear equation? Anybody can quickly answer me before we finish today's lecture. Anybody can tell me, is this a linear equation? Anybody can say? Is this a linear equation? How do you think? Well, this is not a linear equation because here you're going to have y squared. If it is y, it's a linear equation, but you have y squared. So this is not a linear equation. And for nonlinear equations, there is no other method to solve it, but rather separation of variables. So you're going to write this equation as dy over dt is sine t y squared, that you separate variables, 1 over y squared dy sine t dt, you integrate and find antiderivative, put the initial conditions there, you get a solution. And so that's kind of a very simple exercise, just to telling you, right, that sometimes you need to be able to choose the right method by yourself. Okay, so this is going to be part of the exam, is that it's not going to be exactly telling you which method to use, but most of the time you have to choose the right method by yourself. However, there's another type of problem that you're going to see on the exam, that they're going to tell you which method they wanted you to use. For example, please use integrating factors to solve the following equation. Then you have to stick to the method that they wanted you to use because they want to test that. Okay, so that's kind of what I want to say about the integrating factors. Okay, so let us come back to the next lecture, and we're going to continue with our discussion of first order equations. Okay, so let's meet in the next lecture.